Okay. Apparently, the computer still wants to take a break. Okay. Maybe I take this occasion to say a bit more about the midterm test. Someone asked about the format of the test. I think I would send an email, but since you have been so faithful here, how can I not reward you by letting you know first, right? So the test will consist of two sections. Section A, which is multiple choice questions, and there will be 15 questions, and there will be no penalty for a wrong answer. I mean, the other instructor is kinder, so he convinced me not to penalize you guys. So Section A will consist of 45 marks, and then Section B will consist of 3 questions, short questions. We just want the answers, okay? And each question in Section B might consist of multiple parts, A, B, or C. Each short questions carry 15 marks. So in total, Section B will also consist of 45 marks. So the total marks for the test will be 90. So for your time management estimation, would be half an hour for Section A, and then half an hour for Section B. Now, since we don't penalize you for multiple choice questions, if you are not very sure, you can hold on to it until you are asked to submit your, when we are collecting your paper, then you quickly just try your luck and write down some one of the A to E, right? Don't write F or G or H. I mean, of course, then you are pushing it too fast, all right? There will be a little bit of, we will announce the sitting plan in as much as we do. Those who are taking the test, the bulk of you, taking the test from 10 to 11, so we'll be seated in, try to sit in one big group. And then for those who have to take the test early and then have to leave a bit early, then we put you on another sections. Now, we will not be able to take over the entire hall. There are Section A and Section B of the hall, and we have to share it with some other module. I think they have about 200 some. Yeah, I can't put it up. Oh, okay. Can I continue? You just. Oh, hi. Something. Okay. So we can't occupy the whole hall, so that is the tricky part. And the other module is holding their test also from 10 to 11. So we will put those who have to take the test at 9:45. So there are actually 3 time slots for you to come in. One is 9:45 if those that have a test right after our test, or those who come in at the usual time at 10. And then, oh, good. What did you do?
I think the window crashed.
Oh. Okay, I think that would be good. Yeah. Thank you so much. Okay, so students can come in at 9:45 if you have a test right at the back of right immediately following my test. I think now the arrangement is the test is actually 11:30. So I'm quite sure you have enough time to go over. And then another, many of you are, the main bulk is actually from 10. So we'll probably allow you to come in about 5 minutes or 10 minutes early, so you can come in. And then the other smaller group is you have a test before 10. So we allow you to come in at 10:15. And so everyone will have everyone will have an hour for the test, all right? Now, one thing you have to note is that towards the end of the test, especially for those taking it from 10 to 11, because of the logistic of collecting the answer sheet and all this, so I think the last 15 minutes, that means 10:45 to 11, we won't let you take toilet break or even leave, so that we can actually collect everything, and then we'll count them before releasing you out. So we will try to, all the tutors will be helping us, so there will be 7 of us, including the 2 instructors. So we hope we'll be able to get everything done quickly. One of the things that hold up the collection time is students try to still keep on writing when we ask you to stop writing. Now, this is not good. If you continue to write with even we warn you not to, you might be penalized, all right? But this is where it's being held up in the collection process. So if everyone is cooperative and then you really stop, so we will collect them in much quicker. All right. So what other things I need to, what other things you think you want to know about the test, or your friend may want to know? You will be your friend anyway. So any other things? Because if you send me emails, it would be, I try to disclose the information to everyone rather than, on an individual basis. I think that would be fair information to everyone. Yes? I understand, I myself would like to give you some practice questions, but I'm not sure because one of the concern from the lecturers before me is that actually we will, don't tell anyone, we will recycle some of the questions, especially multiple choice questions. It is very difficult to set good multiple choice questions. So that is one thing that holds us back from doing that. But I think we'll probably do so by uploading portions of the final exams, not at this moment, but towards closer to the end of the module. Probably will take a bit of here from the past papers, so that at least you can have some practice. Okay. Yeah, I really, I myself do not think it's ideal not uploading some practice questions for you. So, yeah. Any other questions? Okay. All right. After the break, I actually forgot where I was. I'll keep moving until where I stop. Right? I think I've talked about marginal distributions. Is it? I have covered this, right? All right, thank you. So we haven't done the conditional distribution. Okay, just the definitions. All right, thank you. So I'll start from here. There is a parallel for probability of an event to, say, a density function or a distribution function. And then probability of two events, I mean the joint, meaning the intersection. And then the parallel is a joint probability density function of a joint probability mass functions. And now, once we have two, the probability of A intersect B, then we introduce a concept of probability of A given that B has occurred. So that is the the progressions. So similarly, so we introduce one variable and its corresponding probability mass function or density function, depending on whether it's continuous or discrete. Then we talk about joint probability mass function or joint probability density function. And then now we wanted to define the conditional distributions, all right? So parallel to the conditional probability. So consistent with the definition of conditional probability of events, we can define conditional probability mass function. So we define one first. Oh, okay. I think I have done this, right? And I have done the table. So I think I've done the continuous case. So basically, the definition is, this is the notation. Now, you have to be a bit careful about uppercase and lowercase. When you type, you probably won't make mistakes. These are the mistakes that students make. The X and Y here, the subscript, refers to the random variable. And in this module, or in most probability courses, we try to use uppercase for random variables, okay? And then use small x or small y to denote the values that the random variable might take. So here, in the discrete setting, I'm basically evaluating that x, the random variable x, is taking on the value small x, okay, given that the random variable y is taking the value small y. So this is the meaning here, all right? Now, another common mistake that students committed when they write, especially in the past, this is a vertical stroke, all right, rather than a backslash, all right? So, of course, even, when we are writing, my handwriting is very poor. So sometimes it's seen as a backslash. Why am I so particular about this? Is the backslash has a special meaning, especially when you're talking about sets. Because A backslash B means that it's the set minus. So all those elements in A that are not in B. So it does have a meaning in itself. So that is why we don't want to confuse the two notations. So the definition of the conditional probability mass function, as before, is actually the ratio of two probabilities. So it is the probability that x is equal to small x, y is equal to small y, over what you are conditioning on. So the right side of the stroke, the vertical stroke, is where you are conditioning on. All right, so this is the marginal of y here at the value small y. Now, of course, this condition is, sort of natural because we are going to divide by some quantity here. So we just want to avoid a division by 0. Okay. The conditional probability mass function of y given by x is defined as this. So this is just changing the order of y and x. So the important thing is which one you are conditioning on. So it is the one that is on the right-hand side of the vertical stroke is the thing that we are conditioning on. So meaning that we assume it has already occurred, all right? Okay, so we have similar to the conditional probability, when your y here is fixed, all right, that is why it is emphasized here. then this is a probability mass function in small x, all right? So the conditional probability mass function is itself a probability mass function when the thing that you condition on is fixed, all right? And so this is just changing the other order, so it is actually parallel. For discrete random variable, so this is the situation here. So now y is fixed, and this is, and then you are summing over all the small x. This is very similar to your fraction, because you are conditioning on the small y. The denominator is in y. The numerator is in x. So when you sum the thing, you are summing the thing in the numerator, so which is okay. But when you are summing over the small y, then it is not okay, because when you sum, say, two fractions, even when they have the same numerator but different denominator, and when you sum it, you don't just sum the denominator, all right? So that is the common mistake here. Okay, so this is just a continuous version, changing the summation sign to integration. So again, we just have to live with it. I mean, distinguishing whether things are discrete or continuous. We use slightly different mathematical notations. Okay, so here, this is the expressions here. So this is actually parallel to your multiplication rule in conditional probability, because in your conditional probability, you have this. So this is the definition. All right? So this is the definition. And now we have the multiplication rule. And so we just multiply these things over. All right? And the parallel is here. So if you have f of x, conditional density, this is given by this. Okay, we have the condition here, positive. But what is the essential thing is we multiply it over. All right, so we have the same multiplication rule here. Perhaps one thing that you have to see, or I want to emphasize, this is not necessarily equal to f of x of this. Just like here, this is not necessarily always true. All right? While this is true, this is not always true. In the same way, this is always true, and this is not always true. And in fact, we are going to introduce independence concept here, just like we are introducing independence of two events. So we'll be defining independence of two random variables. So this is regardless of whether it's independence or not independence, because this multiplication rule is actually followed from the definitions. All right? Okay. Now, here it gives us, again, a way to, depending on the context, if you know the joint density, all right, then of course we'll be able to calculate the marginal, all right? And so as a result, we'll be able to compute this. Now, the multiplication rule can be seen in another way. Suppose you know the marginal of x, but somehow you know the conditional probability mass function or conditional density function in this way, then this multiplication rule says that you can recover back the joint probability mass function or the joint probability density functions in this way. All right? So basically, you have three quantities. And if you know two quantities, you will know the other one. So questions actually revolve around this. Okay, so so far we have talked about this. So I think we have done this, right? Yeah, I'm not. My dementia is just starting, so it's not that serious. So I remember this. All right. So did I go through this? You are not much better. So, okay, suppose an experiment consists of three tosses of a fair coin, with each outcome being equally likely. So I have two random variables that defined on this experiment. One random variable is the number of heads on the last flip. Okay, so what are the possible values of x? We are only looking at the last flip for x, and we count whether we have a head or we don't have a head. So it will be x, the random variable x takes possible values 0 or 1. And whereas y is the total number of heads for the three tosses. So what are the possible values of the random variable y? Now, whenever you see a random variable, one of the most immediate questions would be, what are the possible values? Because this is important, especially when you are asked to calculate the distribution. Because basically, you are asked to give me I want you to give me a table for discrete case. Then the table has to be populated. And so one of the things is to determine what are all the potential values of the random variable y. So y is counting the number of heads in three flips. So one way to think is the worst scenario and then the best scenario. So the worst case is you do not get any heads. And then the other case is you get all heads. So then you decide you can get 3 heads and 0. So you still have to think whether 1 and 2 are realizable. So of course this is okay. So basically this is the a brute force table. So I have 1, 3, 0, 2, 1, 2, and so on. Now of course when we form the table, we have to collapse those that are the same. So for example, this part and then this part. All right. So we have to collect them. And similarly for the others. All right. So we come up with this. So these are the possible values. So that's why I say one has to determine what are the possible values of x. So this is 0 or 1, because x is referring to the number of heads in my last flip. So I can only have either a head or no head. Here it is from 0 to 3. So from the previous table, I can now construct this a 2 by 2. It's a square table here. All right. So I think now it would be quite easy to do that. All right. So now what do we need? Okay. So of course this is just doing these calculations. Now realize that we are conditioning on 1. So basically another way to do it is this. Better to work with the table. Okay, so okay, so this is x. I only need to focus on 1 anyway. And so this is 0.5. And so this is 0, 1/8. And then this is 2/8 and 1/8. So the conditional would be y here. Okay, this would be 0, 1, 2, 3. And here I need a little bit more space. This is condition on 1. So what I do is this is the row total, and then I use basically renormalize the entire thing so that this will add up to 1. So I divide it by the row total. So this would be 0, and this would be 1/8 divided by a half. So we can simplify it later. All right. So this is the idea here. So if you were to do the other one, then of course there is no such thing here, 0. Then you have to work it out and then divide each entry by this marginal value. All right. So so I guess this is more intuitive than the next slide. All right. Okay. So this is how we get this table. Okay. So now consider example 2 on the slide 420. We wanted to find out the marginal and then the conditional here. So anyway, so I will have this, all right? So the marginal is to sum over all the possible y, and y is 1, 2, 3, and the expression is x times y over 36. X is fixed, all right? So x is also for 1, 2, 3. And so we are summing this, and this is just simplification. This is x over 6. And so I will have this, all right? And so this is just calculating this, and this is y over 6. Now, why we went through this for one good reason. This is an example that we are going to introduce independence of the two random variables, and this is an example for that, all right? So we spend time in doing this, all right? Okay, so now this is a joint density function. So this is a continuous case. So I have a joint of this. So actually, if I were to ask you this, you still have to do the marginal of this at least, all right? Of course, you don't have to do this part, but you have to do this part because to find this, you remember is the ratio of this function and the marginal. So you are forced to do this, all right? So this example is to compute the marginal of x. Okay, so for first of all, maybe it's good to just, this is a very simple situations, but I think it is always a good practice to do it. So I'm just working on the xy plane, and then when x is between 0 and 1, and then this is 0 and 2. So over here, the density function is of this form. And then elsewhere it is 0, all right, sort of like this, all right? So So in other words, when will you are actually, what you are doing is the marginal. Now when your x is somewhere here, you imagine you are adding up everything along this line, but the function is 0 here, so you will accumulate 0 things. And similarly, when your x is bigger than 1, you will also have 0 here. So the only the focus should be when x is somewhere here, because this is where you will accumulate things according to this formula. All right. So you will be integrating over all the y here. All right. But from minus infinity to here, you can ignore it. All right, because the joint density function is taking value 0. And then from here all the way to plus infinity, this is 0 too. So what remains to integrate is just along this segment of the line, all right? So this is what is actually done there. Okay, so that is why we have this, all right? So this is coming from the fact that I actually draw the square earlier, all right? Now, of course, if you don't want to, then, of course, the focus would be here, right? Because otherwise means when x is outside 0, 1, it would be 0 entirely. So when you integrate, it won't show up, all right? So fx of x will be just integrating over the entire thing from minus infinity over infinity, the red line that I draw. But now you have to restrain yourself from 0 to 2, because that is where this formula applies to. And because x is now between 0 and 1, and y is between 0 and 2, so the joint density is given by this. So the next thing is just straightforward integration, and so you will have this, all right? And this is true only for x is in this interval. So, okay, so now we are this slide filling in the detail that I mentioned earlier. So this would be 0 when it is outside the interval 0 or 1, because the joint density is equal to 0 throughout all the y. So as a result, this is given by this, all right? Okay, now at this module, we want to emphasize a good habit, because a density function is referring to the function defined on the entire real line. So even though this is the main thing, and even if you might have spelled out this, what we are looking for would be you have to tell me what is the value when it is outside this interval, or even though it is trivial, it's 0, but it is a good habit to do so. You can express it in this way, or you can just simply write f. You can just write here, and then this, and then when x is otherwise, it is 0. Rather than in this form, you can write it in a sentence. I think that would be fine. But I mean, if you write it this way, I mean, it is a perfect answer, all right? So similarly, the marginal density of y is given by this. Okay, so now it is just first of all, we have to pick the x that is between 0 and 1, because we don't want to divide things by 0, okay? So this is not needed. So I have a first condition to check, okay? X has to be in this range. And then after that, this is still a function, but a function in y. And x is fixed, all right? So this is the viewpoint here. So x is fixed, and it would be a function in only one variable and in y. And now we plug in whatever we know. So this is from our previous slide. So for our marginal x, and so and this is the joint, all right? So I think we just simplify a little bit. So there is a factor 3, one third both sides. So we pull it out. And then there is a factor 2 here in the denominator, and so that reflects here. There is a common factor x in the numerator and the denominator. We cancel it out, all right? Because, well, of course, we have to be a bit careful. Okay. If you really want to find fault, here is your opportunity. X has to be strictly positive, all right? Because if x is equal to 0, the marginal density is also equal to 0. So to be absolutely faultless, we have to say x is strictly bigger than 0, less than or equal to 1. All right? Is that all right? Now this is the embarrassing moment disappear because the x is cancelled out. But this cancellation only is sensible when x is not 0. Otherwise, you are dividing 0, you are cancelling 0, which is, I mean, it's not right to do so. All right? But these are some, I mean, minor things. Now, of course, you say, when is it minor, when is it major? Again, the same thing. I will decide. All right, sorry. I mean, wait until when you are teaching, then it's your turn to decide. Okay, so so there is a little problem here. So that is what we were saying. So let's just don't talk about this. All right. So you can strike this out. So when x is equal to 0.5, then we just plug it in this way. Now, strictly speaking, this part is not wrong, because what happens is if this is 0, this part will also be 0. Okay, it implies this, because this part is the accumulations of everything in y. So if this is already 0, so this part will be 0. So you will have a 0 over 0. And in mathematics, we can, in some occasions, we can define it in an arbitrary way, as long as it's consistent with the big picture. Sometimes we can't do that. Sometimes we can. All right. So and that is the situation here. Okay. An example, and this is a jointly continuous example. So let me look ahead first. Okay, so I think I will go through this example, and then we'll have a break. After that, we'll continue with the other example, and probably we will introduce independent random variables. So a fast food restaurant operates a drive-up facility and a walk-up window. On a randomly selected day, x is the proportion of the time the drive-up facility is in use, meaning that at least one customer is being served or waiting to be served. And y is the proportion of time that the walk-up window is in use. Now this is about whether I mean, you can think of it as two counters. One is for the walk-up, one is for the drive-up. So one of the main, this is a very broad subject. It's called queuing theory. Again, the drive-up facility can be a server. I mean, in your guys' area. So the customers are now just computer jobs coming in. All right. So you have just two different kind of jobs that are arriving at two different servers. I mean, so tons of questions people want to ask is whether the server is always busy or the server is always idling. Either way is no good. All right, so there is some way to, so there is a design thing on your part, but some of this information is needed. So now we go back to the fast food restaurant, but the fast food restaurant is just a context for these applications. So so the Jordan density is given by this, and now see what we are interested. So find the probability that neither facility is busy more than 1/4 of the time. So that would be probability of X less than or equal to 1/4, and Y is less than or equal to 1/4. So B, find the probability that the driver facility is busy more than 1/4 of the time, but less than 3/4 of the time. So here we are singling out on one of the random variable. So we are looking at X. So in this case, we need to look for the marginal distribution of X first in order to answer our questions. Given that the drive-up facility is busy 80% of the time, what is the probability that the walk-in facility is busy at most half of the time? Now, we will interpret this a bit later, but this is going to be a conditional probability that we are looking for, all right? And so on. So now we just need to rephrase it. So the story problem is this. So now I think you should spend time in translating what the story is asking you in this way, all right? So here they're asking the drive up and the window walk up are both busy 1/4 of the day. So this is this, all right? And then now, of course, I have mentioned it many times. The next thing you have to watch out is the integration limits, all right? So I think you should spend time in formulating this, all right? And then, of course, once you formulate it wrong, you won't get the limit right, and everything will be wrong, all right? So spend enough time in translating it into here. And then the next thing you should pay attention is the integration limits. The actual integrations, of course, is important for the final answer, but at least you get your, halfway through. But if you get your limits wrong, things are very, your answer is definitely wrong. Even if you get the right answer, that means somewhere wrong must have happened. In order to get the right answer, or you copy it from someone else. All right. So this is rather straightforward. So I guess I'll leave it to you. And then the reason why we wanted to work this out is because this is the formulations. The formulation is we are interested in this. All right. So you have to do this. But you can also, so this is the way this lecture notes is solving it. But you can also do it the other way, all right? Slightly different, but it's the same, all right? So let me rephrase it. So this is what we want for B. Sorry, this is 1/4, and then this is 3/4. But this is the same as, basically you have no condition on X, on Y. So you can think of it this way. Then this is just a double integration again. So this is 1/4 to 3/4 f of x, y, dx. Okay, let me put it this way. This is 3/4, and this is 1/4. This is minus infinity to. So I integrate y first, x, all right? But this will be the same as, because y is ranging from 0 to 2, and then the Jordan density is the Jordan density is 6/5. So basically, you can do it this way, all right, in one go. But of course, in the process of doing this, you are actually calculating the marginal of x. So, so this is the situations here. So even if it does not occur to you that you have to calculate the marginal of x, if you see it as a joint situations, so you fill in the missing link here. And of course, basically, there is no condition on y, and so on and so forth. Okay, but you'll be rewarded for calculating the marginal, because I think part C needs something on this. All right. So this is the first thing is to reinterpret the questions in our notations. All right, because everything later would be just in terms of the notations or the mathematical formulations. So the key thing is to spend enough time to reinterpret the question asked in terms of our random variable. All right. So this is saying that given that the drive-up facility is 80% busy of the time, and I want the walk-up facility to be at most 1/2 of the time busy. So this is just being translated to this. At most would be changed to y less than or equal to, and then this is what is given. So the rest will be just rather straightforward. So so we don't want to overdo it. All right. And so as a result, what they do need now is to calculate this is sort of like a cumulative probability. You need the density, basically. So that is how why we need to look for this. All right. So maybe I backtrack. This is the problem that we wanted to. And in order to calculate this, I have to know this guy in order to do the integration. Okay. And because of this, then I have to work this thing out. All right. So this is the the process. Okay. So the answer is 53/136. And now we wanted to find out. This is actually more interesting because this is the kind of questions that we are curious. If the drive-up facility is 80% of the time busy, what is the average proportion the walk-up facility will be busy? All right. So this is calculating the average. The average would be just, I think we missed out the -infinity to infinity here. And so y of this. But now we have to restrict it to 0 to 1 because y only takes values between 0 and 1. And so the rest will be just integrations, all right? So I guess maybe we should have a break. So let's please come back at 11, then we'll continue with whatever it is. Okay, so let's do one more example. Now, maybe I should say it this way. Some people think of probability as two hands. One hand is the left hand, where it is, it's a labeling, all right? But don't take it too seriously. People who are left-handed usually are witty, and they do things in a very, indirect way, but it's very fast. So probability has this character. It's the formulations or a way of thinking. So if you think it right, it is actually very, to the point. And then there is the right hand of the probability. It's just do it. All right? It's just hard work. Integration, even though you know the integrand, the limits, you still have to do it. All right? So even if it might be straightforward, you have to just do it. All right? So that is the right hand and the left hand analogy. So at certain point of some of these examples, especially the lecturing part, I wish I could just lecture on the left-hand part. Not that I'm a left-hander, but it is actually where you learn. But certain part of the right-hand part is you really have to execute the calculations. It's just like, I think in computer science, you think of an algorithm. So you have an idea how to proceed. But eventually, you still have to code it. The coding part is really, I think, is boring and can be very, easy to make mistakes, especially for low-level kind of a compiler. So this is where the tedious part. But you need both parts because unless you, one day when you rise up as like a supervisor or managerial level, you just give your idea and then let all your people working for you to do all the hard work. Then they do the coding. And usually this is the situations. Young people do the coding, all right? Old people just give ideas, all right? Sometimes the ideas may not work. Then you go back and say, this old guy doesn't work, all right? So, but anyway, there is a left hand and right hand here. But in life, actually, there is a left hand and right hand in both situations. And there are people, especially the mathematics people, they enjoy doing the math thing, without the left-hand side. Okay, so here this is another one. So let xy be uniformly distributed over the triangle with the boundaries 0. So this is a triangle, so we have to graph it first. All right. So this is already kinda telling you that it is a triangle. So the first thing is you have to define the boundary. Okay, so we draw this part first. Y is 0. Okay. And then y is equal to 2. So this is, so I have already drawn this part. And now x is 0. So x is 0 is this part. Okay. And then x is equal to y, this part. So x is equal to y would be this. Okay. So now here, basically, we are talking about one of the triangle here. But we have to decide which one, all right? So one way to do so is to pick any convenient point, not on this line, because so you pick 2, 0. If it's 2, 0, then this inequality does not hold. So it means it has to be on this side, all right? So this is the triangle that we are looking for, all right? So I think, did they draw it? Yeah, something like this. So this is how we construct the orange triangle here. Okay, but now this is almost the first thing you need to do. Otherwise, you wouldn't be able to proceed. Yeah. Oh, sorry. No wonder you can't see the orange. All right. So this is the orangey triangle that we are referring to, the thing that I just draw. So now the tricky thing is it doesn't tell you the joint. Oh, there is two joints here, so delete one of them. Find the joint probability density function. Uniform distribution means the density function is a constant. Now, what is the constant? Okay. So now let's refer back to this orange color. So now I have a density function. This represents a surface on top of this triangle. Okay, but the fact that this is uniform means that the surface is flat. All right. And so now we know the volume underneath this surface over this triangle has to be equal to 1. All right? So, so the volume of this triangular block, do you see what I see? Okay. Okay, so something like this. Okay, I draw it this way now. And then this part, right? And now I have a surface, and that is the fxy. And then this is now also flat here. So this is this part, actually. Yeah, okay. Okay. Okay, this is like your block of cheese or your sandwich, all right, something like that. So now this height is equal to c, let's say. So the total volume of this sandwich should be equal to 1. Okay, and the volume is equal to the height times the area of this orange triangle. This orange triangle is half times 2 times 2, right? Because this is the height of the triangle. This is the base of the triangle. So so C would work out to be half. Okay, and so that is how it is constructed. Is that okay here? I think the rest of the thing is probably very repetitive, but I think this is probably a little bit of new element in it. So this is actually how it is done here. Okay, so as it turns out, finding out the joint density takes a little bit of effort in this case. All right. Okay, this is actually explained here. Okay. So now we are, yes. Oh, sorry. Yeah. Okay. So actually, because I was, I mean, it's a little different style in thinking. So I present the working in a bit different order. So this is actually how the half comes about. All right. And also the rectangle is actually drawn here. Okay, so so actually you don't need to do all this because in effect because it is a constant, so it is the volume or the k times the area of the region that you are integrating. So. Okay, so I guess you are okay with this. And now to work out, okay, and now we wanted to find out, okay, so I think this is just trying to explain it, the equation 3.3. So I guess it's pretty clear, right? I mean, you don't need to do the integration here. If the problem is a little bit trickier, then you have to. But in this case, we can have a geometric interpretations. So if you are fine with it, then you can just skip. Okay, you can basically keep this line, and then k is determined by this. And so you can jump right in of the area of the triangle, and then you can determine the k equal to 2. So you can skip all these calculations. Now we are interested in looking for the marginal probability density function of x. So this is integrating out all the y, basically summing up all the effect due to y. Here, the first thing you have to divide into two regimes, whether x is between 0 and 2 or otherwise, all right? When it is otherwise, this joint density function is 0 over all the y, so your integration will be 0. Now here, this is when it is between 0 and 2, this is half, okay? But the integral, the lower limit is x. So this is the thing that you have to be careful, all right? It is because this is x. The reason is this. Okay. So now you fix an x. So you are integrating over the entire thing. Only here, the joint density function is half. Elsewhere is 0. So you have to start from here, end up at here. So the ending point is 2, because this is x2, and this point is x. So you have to find out what this is. But this is the line that you are looking at, x equal to y, so this would be x as well. So your y would be from x to 2, all right? Okay, so this is, I think, a very a boogie trap. I mean, if you are not being careful at every stage, you might simply make mistake, and then all your remaining part C and part D or whatever would definitely be wrong. All right, so this is just straightforward integration problem. Yes.
How did they go from the y over 2 squared to 2 minus x over 2?
Oh, okay, this is a notation. It is, it should be y equal to 2, indicating that after your integration, you substitute the upper limit and the lower limit into it. Yeah, it's not, I mean, it's, the notation is a little bit confusing. I don't know. Usually, but I think throughout this module, we will use a square bracket. But after, say, you integrate these things, suppose this is an antiderivative, then people sometimes use it this way. All right, without the bracket, but just a long vertical line in this way. So the notations vary from place to place, but I do agree that we should have y equal to 2. Okay, let me correct that. Okay. All right, so we substitute that thing in. Okay, so this is how it is worked out. And now for this, again, you have to be careful about where you integrate. Now you integrate horizontally, and your y is fixed. When y is fixed, your starting point is from the y-axis, that is x equal to 0, all the way to the line, the diagonal line x equal to y, so it is half here. So I have this. All right? Now, in a way, all these integration things are like your high school stuff. Strictly speaking, it is not very probabilistic, but somehow we need to do it, all right? So maybe, looking back, what you learn about calculus is useful. Maybe this is the encouraging part. I mean, you wonder why you have to do all this integration. Now it is in the real context. You have to do it, all right? Otherwise, you think that this is all the mathematics examples or problems. All right, so I think this is rather straightforward. So I skip this. And so this is by definition, and it is also rather straightforward, and so on. All right, and okay. So, all right. Okay, right? I hope I won't have a protest here. Okay, so this is again similar. Okay, so this is the part that I'm looking forward to. If you think one of the main distinction of probability from other part of mathematics is the concept of independence. You can think of all the joint distributions and all this are basically analysis or calculus. But in calculus, we don't have the concept of independence or dependence. So this is very distinctive in probability in itself. Now, I mentioned before that in a lot of calculations, even in research paper, when people are not able to calculate joint probabilities, they make a very risky assumption that they assume they are independent and then do the calculations. Mistakes can be found everywhere, even in court cases where, the expert witness are unable to calculate joint probability. And then the expert assume it is independent. And then so they give a very small probability of certain evidence. And that the defendant was jailed, because of the calculations. Only when it is appealed that the calculations was pointed out wrongly. So this really is a very major mistake. And in research papers, even in very reputable journals, people do make mistakes. I can understand, I'm not making excuses for them, but I can sympathize them. They have been working for 1 or 2 years on a project, and then everything is hinged on 1 or 2 calculations, and they can't calculate it. Well, make simplifying assumptions, but sometimes the simplifying assumption is really oversimplified. All right, so that is where the mistakes are. And in science, not everything is correct because sometimes people do put a lot of things under the carpet. All right, so we extend the idea of independence from events to random variables. So this is the definition. Random variables x and y are independent if and only if the joint probability density function or the joint probability mass function is the product of their marginal probability mass function or the probability density functions. So this has to be true for all x and y. So this verification is actually true for all x and y here. Now, maybe I think to illustrate this, but I think we are going to see the example. But I wanted to reinforce what this definition is. So I will make something a little bit general. So, but you will see the example. X and y are discrete. So basically, it would be a table. So this is y1, y2, yn, and then this is x1, x2, xm. Okay, so now how do you calculate the marginal? To calculate the marginal is actually adding up this row to get this marginal. And so you also have this, and you also have this. And so as a result, you also have the marginal of y in terms of the table. Okay, so the independence requires this. fxy, xy here. So one of the x, one of the y, for example, this, and here. So this entry, this has to be true for all entries in the table, comes from the product of the marginal here and the marginal here. So every entry here, you go back to this row total and the column total. This entry is the product of these two numbers. And this has to be verified for every entry in the table. So this is it. So this is the definition of the independence. So the assumption of independence is really strong because you have to verify all the m times n entries here in the table. All right? Okay, so this is it. This is checking the independence. Now, why is assuming independence or knowing that it is independent is very useful? Because if you know it's only, so you have to check m times n entries. But if you are, suppose we do it reverse way, suppose we know that x and y are independent, so you do not know the entries of this table, but you are only told the marginals here. You are only told the row totals and the column totals. If you have independence, then you can populate every entry here. So this is the usefulness of independence. It's not because it is useful, then therefore we assume it. So whether they are independence or not independence depends on the problem. But if the problem ensures you to know that x and y are independent, then all you need to know is these numbers. Now here, how many numbers do you need? You basically, here you only need n minus 1 number. Why? Because they add up to 1. And here you only need n minus 1 numbers. So, so altogether you only need m plus n minus 2 numbers. And then you can populate the entire table. Now suppose you do not know independence, then how many numbers do you need? You know adding up all the entire table gives you 1, but that's the only condition you have. So you have m times n minus 1 here. So you have to know many more numbers. For example, m equal to 5, n equal to 4. So the number that you need is only 7, but here you need 19. All right? So, so in reality, if you know x and y are independent, say for example, okay, I often don't have a good example. If you do not know they are independent, then when you do survey, you have to look for m times n minus 1, 19 values in order to count them. All right? But whereas if you know that they are independent, then all you need is to single out all these numbers. Okay, so you only need to estimate this. Once you have a good estimate of this, then you will have a good estimate of the entire table. So, so independence does simplify a lot of things, but it is not because we want to simplify our calculations, therefore we impose independence. Independence is inherited from the problem itself. Okay, so this is the meaning of this. So basically, this is a row total, and this is the column total, and this is an entry in the table. If you think of x and y are discrete, if they then you can extend this to a continuous case as just a function, all right, instead of a table. Okay, now another important thing is that similar to our conditional probability, it says that knowing that the random variable big Y equal to small y is not helping you to predict the marginal of this, all right? The probability that x is equal to small x. So what does this one mean here in the discrete setting? In the discrete setting, x and y are discrete. But this will give us an idea. So this is actually equal to this. This definition is independent of whether they are discrete or continuous. So this is the same definition. But when it is discrete, it means this. Okay. Now, in a lot of our notation, the comma means I have two statements. Okay. So if I have a few more commas, means I have so many statements. And all the statements have to be true. So in a way, this is actually and here. All right. So I have two statements, and both statements have to hold. And so this is just our usual conditional expectations. All right. So here it's saying that if this is the case, this is equal to this. Okay, so what it says is that knowing the x here is not helping you to predict the other variable. Now here I'm using this example, but this is not independent. X is the height of father, and this is the height of son. I mean, say the elder son. Then we know that they are highly dependent. So here, if you know the son's height, if you know the father's height, you have some idea that the son usually are taller. And if you know the father is shorter, then you generally have a prediction of the son's height is shorter. So they are not independent here. Okay. So in a way, independence are very helpful to do calculations. But in terms of discovery, we actually want dependence very often. Okay, for example, I want to know a disease whether it has a relationship to a certain gene. Now, if that gene has nothing to do with the disease, studying that gene for that disease purposes is futile because it's not going to help you. So all people are interested is to find out genes that are associated or that are the disease are dependent on this set of genes and try to understand. So in terms of scientific discovery, we are actually interested in dependence. But in terms of a lot of calculations, it is much easier to do with independence, all right? Okay, so here it says that knowing that y, the random variable y is equal to small y, will not change the conditional density function, and it is still equal to x. All right? So random variables that are not independent are said to be dependent. Okay, so let me go back here. As long as you can find a pair of x and y so that this inequality is not true, then x and y are dependent. All right. So you will see dependence random variable occur, probably much more often than independence. Okay, the product of the two positive functions give a function which is positive. Okay, now here, the remark here, it wants to say, let me see. Okay, I don't know. Let me see. the product of two positive functions, x and y, give a function which is positive on the product space. Product space here refers to the plane, xy plane, all right? Such that if this is positive and this is also positive on A2, then this is also positive here. So I guess this formulation is a little bit abstract, but let me draw it out. So let's say A equal to 0, 1, union 2, 3. So this is the interval 0, 1, and then 2, 3. And then this is A1, A2, say also 0, 1, union 2, 3. So this would be 0, 1, and then 2, 3. So the product of A1 cross A2 will be just this much. Okay. Okay, so it would be the this set here, all right? So the remark is trying to say if f of x is positive here, and then over here f of y is positive, then the shaded area f of xy will be will be positive over the 4 shaded square. All right. Okay. Of course, the remark is a bit more general than this example. Okay, what about independence of more than 2 random variables? So this is the definition here. Okay, the definition is very, in contrast with independence of n random events, which you have to check a lot of equality. Here, you only need to check just one, all right? But it seems to be easier, but you have to work out this. Now, if you are thinking of n equal to 3, discrete, then it is no longer a table, but it's something like a box, all right? Because the x direction is your horizontal direction, and then x2 is your this vertical directions, and then the x3 is the one that is perpendicular to your piece of paper. So you will actually have a box, all right? And each of the entry in the box corresponds to the density of the probability mass function. Okay, and now the marginal would be adding up the entire things. So I don't know whether it mentioned it. Okay, so this is just a definition. I think we are going to stay with 2 dimensions. So let's say x1, x2, x3, x1, x2, x3. So, all right, and in order to calculate this, you have to have a double sum, x2 and then x3. This is your x1 here. And then the x2, x3 will be where you are adding them up. All right? So this is the situations here. If you are thinking of a box, so if you fix a x1, then this is actually the things that you will be adding up. So adding up over this part, all right? Okay, so when you have more and more random variables together, computing this is difficult, all right? Okay? And so, so a lot of information is already embedded here, and that is why we only have one single equation to check. Okay? Now, this is more to give you an idea that we are able to define it for general situations, but we probably will stay with n equal to 2, okay, for the entire module. Okay, so I think maybe it's time to stop because we will work on this a bit later. All right. Okay. So let me give you an idea what we are up to. So we are going to, Friday, I think we should be able to complete independence random variables. And then we talk about expectation. But now expectations of 2 random variables, so there are many more choices. And one of the other important thing is what we call the covariance function. Okay, and then we will define a correlation coefficient, which should be termed as Pearson correlations. It is measuring some kind of linearity. And this is very much used, all right, in statistics and in probability. And in fact, for discovery purposes, people are specifically looking for pairs of random variables that are correlated, all right? So that what you know about one thing might help you to know about the other things. If they are independent, then there is no hope of knowing the other one by knowing the first one, all right? So this is what we are going to do. And after this, I think, I don't know your high school education, but we are going to introduce something more familiar to you, different kind of discrete random variables. So we will introduce Bernoulli random variable, Poisson, binomial, geometric. And then for continuous, we will introduce exponential distribution, normal distribution, and so on. The highlight would be the normal distribution because in statistics, a lot of test statistics assume the populations are normally distributed in order to get the T distribution, F distribution, and so on for your hypothesis testing purposes. So this will be our highlight here. Okay, so let's stop here.